All right, so I'm going to try a different way of recording this video so that hopefully it can post to YouTube. Today is lesson 22, constant rates revisited. Pretty simple. It's the same thing that we saw in unit 4. Remember, constant rate is slope, and slope is change in y over change in x, or the y per the x. Remember, we want to look for this word per to know that it's a rate, which tells us it's the slope. So we know slope is the per, and the initial value would be the y-intercept. So y-intercept would be the initial value or the starting amount. In other words, what it begins with. So initial or starting amount would be the y-intercept. All right, so let's look at number 1. Peter paints a wall at a constant rate of 2 square feet per minute. Assume he paints an area y in square feet after x amount of minutes. Express this equation as a linear equation in 2 variables. So 2 square feet per minute. I want you to point an arrow to this word per. Remember, it is y per the x, so they didn't even need to tell us that y was in square feet. We could see that y would be square feet, x would be minutes, and his rate is 2 square feet per minute, so we know that goes in front of the x. And if we think of real life problems, did he start with anything already painted? Well, no, they didn't tell us that he did, and so we'll assume the starting point was 0, which means the entire equation here is just y equals 2x. Okay, remembering that is in the form y equals mx plus b. It is. It's just that we don't have a b. The b would be 0. So in sketching a graph of this equation, he starts at 0, and then he paints 2 square feet per minute after that. So if we plug in 1, we get 2. Please make sure that you make a note to look at the scale. This goes by 2, so 2, 4, 6, 8, 10. They went by 2s on this, so always check the numbers that they list on the number lines, just in case they skip count. So they went from 0 right to 2, so we go up to 2 over 1, up 2 more over 1, up 2 more over 1. Or in other words, plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you get 6. So it depends on how you look at that. But there's the slope. Use a ruler and draw the line there. Okay, so there's a graph of the equation. There's the equation, and now in part C, they're going to ask you about some different parts of the equation. So using the graph or the equation, determine the total area he paints after 8 minutes, 1.5 hours, and 2 hours. Note that the units are in minutes and hours. So our equation was that he could paint that many square feet per minute. So we want to make sure that it's all in minutes, okay? Make sure that you pay attention to the units. So this was in minutes, So you want to make sure that everything you would plug in for x is in minutes. So right here where they told us an hour and a half, remember 1 hour is 60 minutes, half an hour would be 30 more, so that means an hour and a half would be 90 minutes. If it's 2 hours and 60 minutes per hour, then that means it's 120 minutes. And then you just go through the process of plugging it in. So 2 times 8 minutes would be that he could do 16 square feet. 2 square feet in 90 minutes, 2 square feet per minute for 90 minutes means 180 square feet. 2 square feet per minute for 120 minutes means he was able to do 240 square feet in 2 hours, 120 minutes. All right, so that's all we do. Again, that's an entire problem just using the equation y equals 2x, and we got that because the rate goes in front of the x. Rates multiplied by x. Let's look at Nathan's problem now. So it says the figure below represents Nathan's constant rate of walking. So let's look at that. Already I can see some corner points. Remember, you always want to look for the corner points. So there's one there, 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 and there. It looks like it goes up to the 4 and then over 1. So they added 4 to the y. They added 1 to the x. So it went up 4 over 1, up 4 over 1, up 4 over 1. Remember, it is always y per x. So this would be in miles per hour, y per the x. And that's his rate of walking. And so we see it starts at 0. The b would be 0, which is okay. And then he changes by going up 4, right 1. So that means our entire equation in slope-intercept form is just y equals 4x, rate going in front of x, and we don't need to put on here plus 0, okay? When it starts at 0, you just leave that off, that's okay. And so our entire equation for Nathan's walking rate is y equals 4x. Now it says Nicole just finished a 5-mile walkathon, and it took her 1.4 hours. Assume she walks at a constant rate. Let y represent the total distance in x hours. Describe Nicole's walking rate. All right, so remember rate can also be found with distance over time, but we're going to relate it here. So it's still miles per hour, distance over time. Hers is 5 miles for 1.4 hours, so that's a little bit different. We're going to use our calculator for that one. So we have 5 miles in 1.4 hours. So we're going to take the 5, we're going to divide it by the 1.4, and that gets us 3.5714, yada, 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 yada. Looks like it finally starts repeating right there. And so we're just going to round that to about 3.6. So that's about 3.6. Since we're just going to be comparing this to Nathan up here, who was a whole number, it's okay to just round. So that means she's walking at about a rate of 3.6 miles per hour. Miles per hour. I'll just abbreviate that way for her walking rate. And so that rate goes in front of the x. It's per the x per hour. 3.6 miles per every hour. And obviously she did not have anything already walked before she started walking, so we don't have anything to add there. So there's Nicole's rate. And then the final question there is just who walks at a greater speed over there on the next page for part B. And so we just compare. He's walking 4 miles per hour. Nicole is walking 3.6 miles per hour. And so it appears that Nathan walks faster. So we're just going to write down that Nathan walks at a greater speed. All right, let's look at another problem. Just note that it's usually something per time. Time is usually always on the bottom. Susan can type 4 pages of text in 10 minutes. Assuming she types at a constant rate, write a linear equation that represents the situation. So she types 4 pages in 10 minutes. There's one way to write a rate. Otherwise, we can change that to a decimal. We could leave it as a fraction too, but let's change it to a decimal. So 4 divided by 10, or 4/10, is just written like this, 0.4 pages per minute. So if we were to write an equation for Susan, it would be y equals 0.4x, 0.4 pages per minute, meaning she writes a little bit less than half a page every minute, because half would be 0.5. Now let's see what this is. The table of values below represents the number of pages that Anne can type y in a few selected x minutes. Assume she types at a constant rate. So here's Anne's rate. So they gave it to us, looks like fractions over here and minutes over here. And actually, I know that you might not want to use fractions so much, but these are nice. These aren't so bad because they have this common denominator right here. Okay, so when we're looking at the change in y, from 10/3 to 16/3, all they did was add 6/3. And 6/3 isn't so bad because that is equal to 2. So what they added from here to here is just 2. And we compare that, so slope is change in y, which is 2, over the change in x, and the change in x here is 3. So it looks like that change in x is 3. So the slope is 2/3, which means we can either keep that as a fraction or change it to decimal. We're going to be comparing these two, and so in order to compare, we want them in the same form. So since we changed that one to a decimal, we should change this one to a decimal. 2/3, if you work it out on your calculator, 2 divided by 3, it is a repeating decimal. That one is 0.6 repeating. For these purposes, we can even just keep it like that. That's easy enough to see. So 0.6 repeating times x. And they did not multiply or add anything else, because if we multiplied 3 times 2/3, it would give us 2. So obviously she didn't have anything typed before the minutes started. So now we want us to compare. They want us to compare who types faster. So we can see that Susan's rate was 0.4 per minute. Anne's rate was 0.6 repeating per minute. And so it appears that Anne is typing at a faster rate because she's able to fill in more of the page per minute than Susan can. All right, so we're going to write Anne types faster because she types more pages per minute. All right. So I want you to try number 4 on your own. This is kind of short notes today. It's just revisiting rate, and remember it's always you know, something with time on the bottom, and we're looking for a rate of change that always goes in front of x. So I want you to try number 4 on your own. Phil can build 3 birdhouses in 5 days. Assuming he builds birdhouses at a constant rate, write the linear equation that represents the situation. I want you to try that one on your own, keeping in mind it would be birdhouses per day. And I think that you can get that done. It'll probably go on to discuss Carl. Yep, there's Carl on the back. There's his rate. So you're going to need to do that part too. And then say who is building those birdhouses faster. So don't forget that little part right there. They included that in there. All right, very last part, number 5, explain your general strategy for comparing proportional relationships. Pretty simple. All we've been doing to compare these is find the rates. Find the rates, so something over time. Greater means faster. Obviously, less would mean slower. So go ahead and try number 4 on your own. Make sure to conference with me if you haven't yet this week. Really practice your y equals mx plus b on IXL. I know that today's was a little bit easier, but you really need to practice that. Today is the last lesson of this unit. Happy studying. Talk to you soon.